Hello students, my name is William Bullard. This is for HVAC Residential Controls. Today we're going to be discussing Unit 11 and the split phase motor. Now, because three-phase power is not available in small businesses and residential locations, the air conditioning equipment for these areas is powered by single-phase electric motors. The single-phase motors used in air conditioning systems are generally one of two types, the split phase and the shaded pole induction motor. Today we're going to be hopping right into that. It's going to be a wild ride. Hang on to your butts. If my slideshow, there we go. After studying this unit, you should be able to list the basic types of split phase motors, discuss two-phase power, discuss the operation of a resistance start induction run motor, discuss the operation of a capacitor start induction run motor, discuss the operation of a permanent split capacitor motor, or PSC, reverse the direction of rotation of a split-phase motor, connect dual voltage motors for 120 or 240 volt alternating current operation, and hopefully be able to identify the terminal markings of an oil-filled capacitor and discuss the proper connection to a permanent split capacitor motor. I know these objectives are very ambitious and it's only a 15-minute video, but we'll see what we can learn in that time. Yep. Okay, so split phase motors are divided up into three categories. You've got the resistance start induction run, the capacitor start induction run, and the permanent split capacitor. Of the three, the permanent split capacitor is a large majority of what you will see in the industry. Personally, I can't think of a single time I've ever seen one of the other two motors. I'm sure I have at some point, I just can't think of one. That said, they all operate on the basic principle of a rotating magnetic field. So, as you can see here, forget the fact that it says two-phase for a minute, and let's just focus on the drawing on the left. So in that drawing, you can see a set of windings labeled A and B, and then in the middle there's a magnet. You can see the north and the south. Now, all electric motors work on a principle that a magnet is basically chasing a phase, or chasing the power. So think of it kind of like a dog chasing its tail, okay? It's never actually going to catch it, and it just runs in circles constantly. So as winding A is energized, the pole tries to get to winding A, but then immediately winding B is energized, so the pole tries to get to B, and then A, and then B, and the magnet just spins round and round, and then work is performed. So, with a split phase motor, like I said before, it is single phase. So you're probably wondering why there's a slide up here about two-phase. Well, two-phase power is actually produced in a lot of other parts of the world, just not in America. So here in America, with a split phase motor, we take single-phase electricity and we trick the motor into thinking it's got two phases, because the magnet will not chase the tail, or the magnet will not spin with just one phase. If that were the case, you would just have a constant magnetic pull. The magnet would just go to that, and it would just be a locked rotor, or that's what it would seem like. Nothing would spin. So we trick the motors into thinking there are two phases, or we split the single phase, hence split phase motors for the title of this. Two-phase power is going to be similar to three-phase power, except if you look on the drawing on the right, now we have two sine waves instead of three, but the concept's still the same. Now, it talks about the two being 90 degrees out of phase with each other. If you're really looking for more answers on all this, we can discuss it in class, but what's important is, notice that you've got the two sine waves and they don't just overlap each other, they don't follow each other directly. They're slightly off, and that's where we get the different magnetic fields that cause the magnet to rotate. So let's hop right into resistance start induction run and capacitor start induction run motors. And here's the thing, they are both very similar and they both operate off the same principle, and that is that the stator winding of both motors contains both a start winding and a run winding. The start winding is made of a smaller wire, and it's going to be placed higher in the metal core material than the run winding. Because the start winding is made with smaller wire than the run winding, it will have a higher resistance. Smaller wires have higher resistance than large wires. Okay, so as these go, and both motors operate on this same principle here, the start winding will only be part of the operation until the motor hits about 75% of speed. We'll get to how that happens in just a minute, but remember that number, 75% is very important. Okay, so with a resistance start induction run or a capacitor start induction run motor, the rotating magnetic field is produced by out of phase currents in the run and start windings. Because the run winding is going to appear more inductive and less resistive than the start winding, the current flow in the run winding will be close to 90 degrees out of phase with the applied voltage. The start winding will appear more resistive and less inductive than the run winding, causing the start winding's current to be less out of phase with the applied voltage. The phase angle difference between the two, which it will be shown in the drawing on the left here, the phase angle difference between the current in the run winding and the current in the start winding of a resistance start induction run motor is generally 35 to 40 degrees. And that's great. That's what the book says. That's what we all know. Unless you're an electrical engineer, this information is not going to do you much good. The important thing is there is a rotating magnetic field because the phases are different. What's more important about these motors, and what I really want to focus on for a minute, is the center picture. Okay, so if you look at the center picture here, you see the counterweight, the contacts. Basically, the way a centrifugal switch, and that is a picture of a centrifugal switch, the way it works is you've got a weight on an arm or some kind of aperture like that. And as the motor begins to spin faster, at some point that weight will be slung out by centrifugal force, hence centrifugal switch. If you're looking for an example of something real like this, we've all ridden the ride at the fair where you stand against the wall and it spins really fast and it pushes you up against it. Same concept, except we're pushing a bar out, and when that bar comes out, the set of contacts in the bottom of the picture open, removing the start winding from the motor circuit. At this point, it just runs on the run winding, continues spinning, everyone's happy. You'll notice on the drawing on the right, you can see the schematic where it shows a normally closed, open on rise, or, so on this it would be open on rise and speed switch, heading to the start winding. Now, the next drawing shows a capacitor in series with the centrifugal switch. Now you have a start capacitor. Same concept as the resistance start, except now we've got a capacitor start. At the same time, once the motor reaches a certain speed, the centrifugal switch will open. This is a common way for doing this on a lot of motors that are not hermetically sealed, as in not welded shut, a motor you can get inside and work on. I can't confirm this, but I am almost positive that centrifugal switches do fail from time to time. It is a moving part. So, in a hermetically sealed or welded shut motor, though, they use what's called a potential relay. I think we get to that a little later on. If not, we'll discuss it in class. But here's on the right is an example of a capacitor start induction run motor. So let's get to something a little bit more important, because those first two motors, like I said, they're not really a thing in the industry anymore. They are still used, but they have their disadvantages. And one of them is that running under load and running with no load, they draw almost the exact same amount of current. They also don't have very much torque, so they're not very good workhorses. They can't do as many things as other types of motors can. That said, if one is sized right for the application and put in where it's supposed to be, they can run for a very long time with very little maintenance. But let's jump into testing the stator windings. This is more important, and this is a big thing with motors. I'm hoping we get to do this in class soon when we get back together. So, testing stator windings is going to be done using an ohm meter. You're going to want to do this, obviously, with power not applied to the system. Cannot emphasize this enough. I know I've already said it before, but never ohm out a live circuit. With an old school ohm meter, you're looking to have something blow up in your face. With a newer ohm meter, you're probably going to blow a fuse and have to pay some money to get it fixed or buy a new meter. Either way, it's expensive, it's potentially dangerous, and it's a waste of time. So disconnect power, and you're going to test the stator winding. Now it shows you this on the schematic. You know, it shows you putting the leads inside the motor. That in real life you're going to be touching the wires, the leads coming off of the wire or the motor. But same concept. So right here on the drawing on the left, somebody's testing the run winding for continuity or seeing how much resistance it has through it. So they've got one lead on the common winding and one on the run and seeing how much resistance is through it. After that, they would keep a winding on the common and go over to start and test that as well and test for the different resistance. And different types of motors have different resistance on the legs. We'll go over that, but it's an important thing to remember is that that's how you test a motor, with an ohm meter testing the windings between each other. Another important test when you're testing a motor is to test all the phases to ground. I don't care what kind of motor it is, you always want to test the phases to ground. So here you'll notice in the drawing on the right, they have one lead touching the run winding. The other one is to the body of the motor itself. You should never have continuity between those 2 points. If you do, the motor's shorted and it's time to get a new one. Some places can rewind motors, but for the small stuff we're doing in residential, it's not worth the money or the time. Okay, so now let's talk about reversing direction of rotation. Direction of rotation of a split phase motor can be reversed, and it can be done that by changing the start winding leads or the run winding leads, but not both. Generally speaking, most split phase motors are reversed in direction by changing the start winding leads with respect to the run winding. Depending on what kind of motor you buy, a lot of PSC motors that you can buy now as rescue motors or aftermarket parts can be reversed easily in the field because they have the start winding wires sticking out the side of it. You swap, there will be 2 oranges, 2 yellows, you swap them around, you get different rotation. Very easy to do. You can do this with other types of motors as well, but I know the rescue motors are very easy to do it with. Either way, you just need to change the start winding leads from one side to the other. Now, let's talk about some dual voltage motors. This is a thing in this industry. You can get a motor that can do 120 or 240 volts. When this happens, it's all because of how they wire it up inside or how you wire it in the field when you get it. If you look at the drawing on the left, it's going to show run windings of that motor wired in series with each other. You'll notice L1 comes in at the top at T1, runs through the first run winding to T2, where it then goes T3, runs through the next run winding out to T4. It's a 240 volt motor. That way you have 2 120 volt windings wired in series with each other. 120 plus 120 equals 240. For some of the other, if you look at the drawing in the middle, you've got a 120 volt motor. You'll notice that the 2 run windings are wired in parallel with each other. That way they both get the same amount of voltage at the same time. Hopefully we all still remember series versus parallel. Now with dual voltage motors, which are not that common, honestly, they probably pop up in a lot of places. I haven't seen a lot of them personally, but I do know that they exist. There are lots of figures. When you do encounter one, the best thing to do is always read the instructions, read the schematic. I don't even believe we have one in the lab that I can help you play with. Let's jump right into a very important point here. Motor power consumption. We've already discussed this once in class, but I'm going to hit on this a bunch of times before the end of the semester. Remember Watt's law. And remember how that works. Remember that watts is the total measure of power. It is volts times amps. The motor does not use more or less energy if it's at 240 or 120. Just remember at 240, the volts is going to be half, or the amps is going to be half of what it is at 120, and vice versa. So either way, volts times amps, you still end up with the same number of watts. So it doesn't matter if it's 240 volts drawing 2 amps or 120 volts drawing 4, you still end up with 480 watts of energy being. Okay, and with that, we're going to have to step over into part 2 of this series. It should be located directly below this one in the Blackboard menu. Thank you.